Welcome. In this session, we'll continue the discussion on how to compute the reactive, real, and complex power of an element. Let's suppose we have an example. Okay, so let's suppose the example is like this. So we have an element like this, and we have another element which is connected in series like this. And the source here connected across this element. So the values of the quantities are the elements are, this is 60 at an angle of 0 volts. And again, remember, this is RMS value. So this is the RMS value of the voltage. Now, let's suppose these are the elements Z1 and Z2. Now the value of Z1 is simply 2 minus J1, and it is measured in ohms. So Z2 is simply given by 1 plus 5J. Oh, okay, so the impedances of these two elements are given. Okay, so our goal is to find what we have to do. We have to calculate values of the average power delivered to each element. Each element means impedances Z1 and Z2. How much is the average power delivered or consumed by these two elements? And we have to find the apparent power supplied by the source. Here, and power factor of the loads. Okay, and power factor of the loads. Okay, that's what we have to do here. All right, so to start the solution, what we'll do, since the elements are connected in series, let's find the current flowing through these elements. Okay, let's get the value of current. So if we know the currents, if we know the voltages across the elements, or if we know the both, we know how to find how complex power is defined, how apparent power is defined, okay, of an element, how the average power is defined for that element. All right, so first of all, what is the total impedance of the circuit? So to start the solution, we say ZT means total solution. Since the elements are connected in series, you can check. So the impedances will add. So the total impedance will be Z1 plus Z2. Now Z1 is equal to 2 minus J1 plus 1 plus 5J. So adding the real and imaginary parts, we'll get this as 3 plus 4J. So this is in ohm. So the total impedance of the circuit is this. All right. Now we know the total impedance of the circuit. We know the voltage across the two elements. So total impedance, voltage divided by the total impedance will give us the current flowing through these elements. So I will be simply given by V divided by ZT. V is simply given as 60 at an angle of 0 divided by 3 plus 4J. ZT is this. Okay. All right, so this is the total limit. Now, if we convert it if we convert the denominator in polar form, so we'll say this is 60 at an angle of 0 divided by 5. If you take square of this and under root, it will be 5 at an angle of 10 inverse 4 by 3 is simply 53.13 degrees. Okay, now simplifying this calculation, it will be simply 12 at an angle of 0 minus 50 is minus 53 degrees. 0.1. We divide the magnitude by magnitude, and we subtract the angles. So 0 minus 53 is minus 53.1. So this is the current flowing through these elements. So this is the total current flowing through these elements, or you can say this is the current supplied by the source. This is the current supplied by the source to this series circuit. All right, so that's the meaning of this. All right, now we know that. So if voltage is in RMS, the current will also be in RMS. So this is the RMS value of the current. So this is in amperes and is the RMS value of this current. Now, in the previous session, we know how do we define the power absorbed by the resistor. We know power absorbed by the this real part of this element is simply this is the resistance of the element, this is the reactance of this is the resistance of the element, this is the reactance of this element. Okay, whatever this element is. So this is the resistance of the element, this is the reactance, this is the resistance of the element. Now this element will consume power or absorb power because this is resistance. So resistance consumes power. Now if we say P1 is the power consumed by the element Z1, now it is given by simply I RMS square. If you remember the definition of power multiplied by the resistance. So let's call it R. Now what's I RMS square? I RMS square is simply 12. Okay, square because it is given RMS. Okay, magnitude of this current multiplied by 2. If you remember the definition from previous class. So this is simply given by I RMS multiplied by 53. Okay, I think I have. Let me check. So it is 12 square is 144 multiplied by 2, that's 288 watts. So this is the power absorbed by the resistance of the first element. Okay. Now the power absorbed by the resistance of the second element, let's denote as P2 will be equal because the same current is flowing through the two elements. So it will be RMS square times R2. R2 is the resistance of the first element. So it will be second element. So it will be 12 square and the resistance of the second element is simply 1. So it will be 12 square multiplied by 1. That's for 144 watts. So this is the power consumed by the first element and second element. Okay, these are the powers consumed by this. Now, what is the complex power supplied by this source? So, complex power supplied or absorbed by any element is simply voltage times the current. So, what's the voltage across the element? So, complex power supplied by this element that is denoted by S is simply V times I conjugate if the values are given in RMS values, because RMS values are given. So it expression is this. V is simply 60 at an angle of 0, and I is simply, how much was the I? Calculate 12 at an angle of minus 53.13 degrees. So doing the calculation, it will be simply 720 at an angle of minus 53.13 degrees. So this is S. So this is the complex power supplied by the source. Okay, so this is the complex power supplied by the source. Now, the complex power we can express as, so S will be simply as 720 cos 53.3 plus J. Sorry, this is 720 sine of minus 53.13 degrees. So this is equal to, how much will be this? I think this will be 432. Please check the calculations. Minus, is this minus or plus? Is current minus or plus here? Current is minus, so it will be minus J. Please check it whether it will be minus or plus. You check it yourself. 585 plus 5. Okay, so this is the complex power supplied by this. Now, can you tell me what is the value of P1 plus P2? So this is the complex power supplied by the source. Now, complex power is equal to real power plus the reactive power. So this is the real power, means the power supplied by the source that will be dissipated by the circuit. Now what's P1 plus P2? 288 plus 144. That is equal to 3. I think that's 432. So that's equal to 432. Check the real part of this. So the average power supplied by the source is equal to the average power consumed by the two elements. The average power consumed by the two elements is 288 plus 144, that's equal to 432 watts. So you can see the average power supplied by the elements, by the source, is same as the power absorbed by the these two elements. So if you remember the Taylor-Jones theorem, power supplied is equal to the power consumed. Okay, so power supplied is equal to the power consumed. Now you can do the same calculation for the reactive elements. You will see the power consumed by the reactive elements will be simply equal to this. Our power stored by the reactive elements will be this. So this is the power supplied by the source. Now if you calculate the power supplied by this, consumed by this, stored by these two reactances, that is 1J and 5J, you will see it will be simply equal to 585. Okay, please do that exercise. We'll see it. Okay, so power supplied by the source is always equal to the power consumed or stored by the circuit. All right, this is referred as Taylor-Jones theorem. If you remember, we already studied this in DC circuits. So this is called the Taylor-Jones theorem. All right, so this we verified that the real power supplied by the source is equal to the real power absorbed by this network. Okay, circuit. Now how do we get the apparent power? Apparent power means simply the magnitude of S. So magnitude of S is simply 432 square plus 585 point. How much? Please check the calculations, and this will be simply 720 VA. If you already know the magnitude of S, you don't need to calculate, right? It will always be same. Okay. Now the power factor. So to compute the power factor, which is denoted by PF, is given by simply either you use cosine of the angle of the power, or you use simply P divided by. So P is 432 divided by S magnitude. I'm talking about 720. This is same as 0.6. Now you can see cosine of 53.13 is equal to also 0.6. So whether you use this one or this calculation, that's it. So this is the power factor of this nodes. Okay, this is now at what power factor these two loads are operating. All right, so this is the calculation that we needed to do. Okay, we needed to calculate the real power absorbed by the two elements that we got as 288 and 144, and we also checked the result that the real power supplied by the source is same as the real power absorbed by the circuit. Now the circuit is composed of two series elements. All right, so I hope you have got the meaning. So power supplied and consumed is always, this is referred as the Taylor-Jones theorem. All right, so let me end this session here. In the next session, we'll continue the discussion of these power calculations.